So, ladies and gentlemen, this is our masterclass on acids and bases. Now, one of the things that I wanted to start off with on acids and bases with everybody here tonight is what hydrolysis is. All right, so I'm going to start on a whiteboard. Hydrolysis is, it's disproportionately difficult for the number of marks that it's worth, but if you're aiming to get top marks for your matric exam, you can't afford to lose the marks for hydrolysis. So there are two hydrolysis definitions in your matric exam. One deals with, in fact, maybe there are a few more if we get a little bit open-minded. One is the hydrolysis that you deal with in your organic chemistry. So you've got a hydrolysis, which is the reaction when you start with a haloalkane and then you react it and you turn it into an alcohol. That is called hydrolysis. There's also technically one where if you take, this isn't examinable usually, if you take an ester, you can split an ester back into the alcohol and the carboxylic acid. That's also called hydrolysis. And then lastly, there's the hydrolysis that we're dealing with in acids and bases. And the fundamental aspect of all these definitions of hydrolysis, hydro deals with water and lysis deals with to break. So it's to break things up by adding in water, okay? So technically, I know we recently did a test at my school. It was the first time hydrolysis came up as a definition. And we went to the extent that anybody who said the reaction of a substance that's broken down using water got a mark for it. But the technical definition when we're dealing with acid and base hydrolysis is that hydrolysis is the reaction of a salt with water. If you remember, I got a little bit more technical with you and what exactly a salt is, and we mentioned that a salt is created when the hydrogen, that should read the, not thy, when the hydrogen in an acid is replaced with a metal. Now, that's the best definition that I've ever heard of it, but it isn't even a very good definition. Having said that, I don't think a salt ever has come up as a proper definition in the matric syllabus. So when the hydrogen in an acid is replaced by a metal. And what we're going to be doing here is we're going to be looking at hydrolysis, which is the reaction of a salt with water. Now, this is probably the worst taught section in the entire matric syllabus. And that's not me exaggerating it. I can honestly tell you I didn't understand hydrolysis until a few years ago, because I was taught very simply at my school that you basically said salt plus water returns backwards into acid plus base. So I took it to be the exact reverse of neutralization. Neutralization says acid plus base gives you salt plus water, then you just write it out verbatim, but opposite way around. Unfortunately, that doesn't give you the right answer at all. So when it comes to hydrolysis, the equation that you're going to get is a lot more complicated than just the original acid and base that you got. So I'm going to teach you this in 3 parts. One of my colleagues teaches it in 3 parts. It actually makes more sense. What I'm about to show you takes 3 parts, 3 steps, and only the last line is worth the 2 marks. So all of the thinking steps that I'm doing en route, you don't have to worry about. So what we usually get asked is either, is a salt acidic or basic or neutral? And then they may also ask you to write down the equation of the salt with water, or to write down the hydrolysis equation, or they ask you, is it acidic, basic, or neutral, and to explain your answer. So I'm going to quickly clear this so that I've actually got enough space. Just quickly take a screenshot if there's anything there that you haven't yet written down. Okay, and I'm clearing. So I'm going to start off with my first example, which is let's pretend we have ammonium nitrate. Now, I find that step number 1 for me is to identify what acid and base made this. If you want to give a name to that step, we call it the neutralization step. So this is like your normal acid plus base gives you salt plus water. I find that if I ever get ammonium, I always link it to coming from ammonia, and my nitrate must have come from nitric acid. Okay, so it's quite a big step for you initially to be able to work out what the two substances that you got were. So I'm now going to go and write here that this came from ammonia plus nitric acid. I'm doing this in word form. You can do it in formula. It doesn't really matter. And that will give us ammonium nitrate. Once again, all of this is extra work that you don't have to put in, plus water. Then what I do is I go in here and I compare ammonia and nitric acid for their strength. So I would say that this over here is a weak base, and this over here is a strong acid. Okay, so that's the first step. The second step, which you could call your ionization step if you wish, it doesn't really matter what it is, but it's us now saying, all right, so this ammonium nitrate is made up of ammonia and nitrate. So it's us actually looking at the ions that make up ammonium nitrate. Once again, all of these steps you can do in your head because there are no marks for them. So what I do here is I say, all right, I start with ammonia and I turn it into ammonium nitrate, and I start with nitric acid and it becomes nitrate. So ammonia was a weak base. If this is weak, this is what its conjugate is. So ammonia is a weak base. It accepts a proton and becomes ammonium. That means that this over here is a strong conjugate acid. Okay? And if this starts off as nitric acid, then when it acts as an acid, it becomes a base. Strong acid will become a weak conjugate base. Okay, and those are the two substances, the two ions that we've got present in our salt. Unlike when I was at school, my version would have gone, if you asked me for hydrolysis, I'd have said ammonia plus nitric acid gives you ammonium nitrate and water, but I'd have written it backwards and I'd have got it all wrong. What you have to do is you either react the ammonium or the nitrate. My advice is whichever one is strong is the thing that you're going to react with water. So my hydrolysis, which is step number 3, is me saying, all right, we've actually got the ammonium and it's going to react with water. This step you will write down. This is for your 2 marks. So it's the ammonium, it's part of the salt, but only one part. You never write down both, it's only ever going to be one, and it's only ever going to be one that's the strong conjugate. So ammonium reacts with water. Here we just said that ammonium is a strong conjugate acid. Since it's an acid, it's going to give away a proton. When it gives away a proton, instead of being NH4, it becomes NH3, and it loses an H and a plus, so it's neutral NH3. The proton that it loses joins with the water, so we end up with H3O+. And this line here is worth 2 marks. Done. Okay, so what I quickly wanted to start with in asking everybody is I wanted to just double check who already knew all of that about hydrolysis. Who already knew all of these steps as well as how to put it together. Fantastic. All right, so some of you did. Good, good, this is looking good. But the point is, if you look here, okay, 1, 2, 3, 4, 6, 7, okay? There's still more than half of you that hadn't quite got the idea. So I'd like to quickly go through the examples with you and to quickly teach you. It's very quick. Once you get the ideas going, I usually find that with my students, I have to do 3 of them like this, and then everybody just shoots and flies on their own after that. So if we're looking at this, we've got to kind of also start asking or answering some of the other questions. Right at the beginning, we knew we had a weak base and a strong acid. So even from that point, we could predict that ammonium nitrate is going to be an acidic salt. Okay, so if the question is quite simply what type of salt is it, acidic, basic, or neutral, you could have jumped in right at this step, figured out what ammonia and, well, what acid and base we use to make ammonium nitrate, and then jumped straight to your answer. Sometimes the question is, what is the pH of the salt? If it's acidic, we're looking for something that's lower than pH 7, but it doesn't have to be a lot lower. It can be just a little bit lower. So I'd usually say that if we're dealing with a salt, it's not going to be between 0 and 3. It's going to be somewhere between about 3 and about 6. Okay. So, and last important thing before I move on here, this exact equation, this one exactly as it's written here, applies whether we're dealing with ammonium nitrate or ammonium chloride or ammonium sulfate. If you think about it logically, if we'd had ammonium chloride, it would still have been ammonia, but this would have been hydrochloric acid, which is still a strong acid, which still would have produced a weak conjugate base. It would have been Cl minus. If we'd instead started with the ammonium sulfate, this would have been sulfuric acid, which still would have been a strong acid and would have produced SO4 minus, which would still be a weak conjugate base. So the rule is with any ammonium chloride, sulfate, or nitrate, this is going to be your hydrolysis equation for 2 marks. So you can sometimes cheat, and if I'd asked you randomly, what happens with ammonium, and I pick any one of the nitrate, sulfate, or chloride, you can immediately jump straight to here if you're prepared to memorize it. Okay, so there are little cheats that we can do around this. Okay, I'm going to do one more, and then I'm going to do the general overview. Please quickly take a screenshot if you need to. Okay. So the next one that I'm going to do is I'm going to pick on, let's do sodium carbonate. Okay, so I'm going to still do those steps that I described to you, which was working out what the acid and base were, and then working out my conjugate acids and bases. But since they're not giving you marks for it, I'm not going to lay it out beautifully. So I'm going to start off by saying sodium comes from sodium hydroxide. Please note, simple rule, any metal comes from the metal hydroxide. Yes, it could have come from the metal carbonate, and yes, it could have come from the metal oxide, but that makes it harder for you to figure it out. Assume if it's ammonium, it came from ammonia. If it's sodium or any other metal, it came from that metal hydroxide. Your carbonate came from carbonic acid. It will take some practice for you to always figure out exactly where they come from, but usually once you've done your conjugate acid-base pairs, they're kind of easy-ish in between. Then I've got to figure out what the 2 parts are, the ionized. So my sodium carbonate is sodium carbonate CO3 2-. So when I combine them, it's actually Na2CO3. Okay, but when it comes down to our ions, we're dealing with Na plus and CO3 2-. Okay, I don't have to worry about the fact that there are 2 of them. It isn't going to impact too much. Over here, the sodium hydroxide came from a strong base. The carbonic acid came from a weak acid. So if this is a strong base, then this should be a weak conjugate acid. I'm going to be dead honest with you. It can't be an acid if it doesn't have hydrogen. So even though in theory it's a weak conjugate acid, the actual bit that becomes the weak conjugate acid is your water. It's not even the metal itself. Okay, so a little nudge, nudge, wink, wink, the metal is never going to react. Okay, over here, if we're dealing with our carbonic acid, that was a weak acid, which means that our carbonate is a strong conjugate base. You then are going to compare these 2, the weak and the strong. The strong is the one that's going to react. So my hydrolysis reaction is the reaction of just the carbonate with water. Okay, to give you, now let's be careful. This is a base. If it is a base, it's going to accept a proton. So it's going to gain an H. Okay, it'll still have its CO3, but since it gained an, oh, sorry, wait. Did I do that right? It's going to be a base. CO3, sorry, that's where I'm wrong. That's a minus. There's that point where you look at it and you're like, I can't put any more negatives on here. There's a problem with it. Okay, so that should have been CO3 2-. When we add an extra plus onto it, it becomes HCO3-. You'll see if you practice chemistry for long enough, when you try and put H pluses on them, you're like, it's not going to be 3+, it can't. And then over here, that would have gained the protons. The proton would have moved this way across. This would have lost a proton, which makes it OH-. Okay, we could go right back to the beginning and see there's a strong base and a weak acid. We do expect the salt to be a basic salt. And then also something I didn't mention earlier, but I probably should have. In the previous reaction, you'll have noticed that one of our products was H3O+. Here, one of our products is OH-, which also re-emphasizes that it's basic. Okay, so this over here, for 2 marks, is the hydrolysis equation. Just as a hint for this one, any metal carbonate, you can assume, especially if it's a group 1, 2, 3, but usually we kind of take it with a pinch of salt and go any metal carbonate, but particularly any group 1, 2, 3 metal carbonate will always be this particular formula. So this could be the same if I did magnesium carbonate or potassium carbonate or any of those, because that have ended up being magnesium hydroxide or potassium hydroxide, which would still be a strong base, still produce a weak conjugate acid, and that would be your overall equation. So as a usual rule, if you get ammonium and then a strong base ending, you're going to do the reaction for ammonium for the hydrolysis. If you've got a metal carbonate, this is going to be the reaction, almost without exception. It seems to be one of those that they do again and again and again. All right, so I just quickly wanted to, there was a question here about, will we always work with strong acids and bases that completely ionize? I've got to cover that still now. In fact, we don't. We can only work a hydrolysis equation with certainty if one is strong and one is weak. If both are strong or both are weak, then we can't do a hydrolysis. So I'll cover that with you in just a second. Can I ask everybody to just quickly copy this down if they need to, so that I can clear everything for you? Okay, so what I was saying earlier is if you have, and this is where a lot of people get taught and they kind of think they get it until they've got to write down the hydrolysis reaction. If you have a strong acid and a strong base, then our conjugates are both going to be weak. If both of them are weak, neither of them are going to react with the water, because what reacts with the water can only be a strong acid or a strong base. So here our rule is that there is no hydrolysis. So if anybody were to give you a question and say something like sodium chloride came from sodium hydroxide and hydrochloric acid, we can't tell over here which is going to, well, both of them are weak with the Na plus and the Cl minus, both are weak, so no hydrolysis occurs. If we have a weak acid and a weak base, then we have a really awkward situation where our salt is going to be made from a strong conjugate base and a strong conjugate acid. And the problem is without knowing the Ka and Kb values, you won't be able to tell which is stronger. So although these do exist, they are not examined. Okay, you cannot tell which is stronger and therefore which will react with the water. So the rule is that we are restricted specifically to cases where they are made from weak acid and strong base. And a weak acid and a strong base, by the way, both of these here produce a neutral salt. Okay, so they can still ask you that it's a neutral salt, but you can't write down your hydrolysis reaction. If it's a weak acid and a strong base, we're going to end up with a basic salt. And if it is a strong acid and a weak base, we're going to end up with an acidic salt. And these are very restricted in which options we can get. So I've already dealt with the idea where we had a strong acid and, a strong base and a weak acid. These would be our ammonium salts. No, wrong way around. Those wouldn't. The ones down here would be our ammonium salts. So this would be your ammonium sulfate, chloride, and nitrate. Okay, and then over here, these would be our metal carbonates typically. And the only other two that they can ask us really, besides the carbonates, the ammonium salts, are that sometimes they're going to ask you for acetates and oxalates. But these two come up very, very infrequently. So usually they're going to test you on the carbonates or the ammonium salts that I've already looked at. Okay, just give me a second. Somebody did ask the question and I've got to try and find it. My cursor stopped moving where I want it to be. Give me just a second. Okay. So the question said, all right, that was a response to the question. Okay, brilliant. Okay, so we're going to do one last example on this with one of the acetates and oxalates, and I'm going to give you a chance to see how well you can answer it. So I'm going to ask you all, and I know I'm pushing my luck just a little bit, what about if I have CH3COONA? That is known as sodium ethanoate. Okay, so my question here, you've got to try and work out what acid and what base made it. And then you've got to try and work out what your two ions are. I'm going to give you a bit of a heads up. It's CH3COO-, which is our ethanoate, and our Na+, which is our sodium ion. And then the only bit that I really care about here is I want all of you to try and write out the overall hydrolysis reaction. Okay, so I'm going to ask everybody right now. I'm going to quickly pause my screen, and I'm going to ask you to try and do that yourselves. All right, go for it and tell me when you've got to the answer. Okay, well done, Ruby. I'm not going to make this too torturous. If you're completely stuck, don't worry. I will go through it just now. Okay, good. This is why it's so important to know your acids and, well, acids and conjugate base pairs. So your conjugate acid base pairs are vital for this. If you don't understand how to get conjugate acid base pairs, then you're not going to be able to work out what your original acid and base were or how to get your conjugates. Okay, at this point, I have a sneaky suspicion that some of the other people I'm still waiting for are either about to finish or have given up, one of the two. All right, that looks good. All right, so I'm going to go through the solution with you now. Sorry for anybody who hasn't yet got there. There's just one question here. Okay, so there's a question here saying they've always looked at it simply by dissociating the two ions to see which ion can react with water. Is there a case where that won't work? Well, I think the problem is how will you know which of the two ions does react with water unless you know all of these steps? So all of the steps that I do are essentially for us to work out which of the two ions will react with water. So I must be honest, you probably, after you've done enough of them, will have figured out that there are only 4 kinds that can react. But I personally have never been able to just randomly look at it and go, it'll be that one without knowing the theory behind it. So I guess if you do it and you consistently get it right, then that's no issue. But the problem is I don't think everybody does it and consistently gets it right. So let's go through this. CH3COOH, the ethanoic acid is my acid, and it is a weak acid. That makes the CH3COO- my strong conjugate base. Okay, I probably at this point could give up and say, all right, that's the bit that's going to react. I don't have to go any further. But I think it's always a smart idea to do it, because if you end up with both of them being a strong conjugate base and a strong conjugate acid, then you'd have to instead actually go and say, I don't know which equation is the hydrolysis reaction because I don't know which one's stronger. So over here, we'd end up with sodium hydroxide, which is a strong base, which makes sodium our weak conjugate acid. And if you remember, I told you it was so weak that it didn't actually have a proton, and it wasn't our acid at all because the water was the acid. So that's not going to be what reacts. So our reaction is CH3COO minus, reacting as a base. So when it reacts with the water, it picks up the proton, which gives us CH3COOH. Because it picked up the proton, that's left without a proton, which is OH minus. Okay, and we can therefore see if they asked us about sodium ethanoate, we could see over here that, I've just got to check that I did get this right. Yep, that it is a basic salt. Okay, and if they ask you why it's a basic salt, your reason, depending on how many marks it's for, is that it's made from a strong acid and a weak base. Or you could say that when it reacts with water or undergoes hydrolysis, it produces hydronium ions. Sorry, hydroxide ions, brain dying. Hydroxide ions. All right. Okay. Ladies and gentlemen, can I just quickly check in at this point with everybody? Does everybody understand all of those little aspects of what we've just been through? Does it make a little bit more sense in terms of what hydrolysis is, what they're looking for? Okay. Now, I must be honest, I told you right at the beginning that I didn't know it until a few years ago. I'm willing to bet that the majority of teachers in this country are iffy on it. Because it's one of those where the only way you'd ever know it is if the teacher that taught you knew it. The teacher that taught me didn't know it. And their logical explanation of, wow, you take your salt and water and go back to acid and base made perfect sense. And the only time I picked up that it wasn't correct is when I kept looking at the memos and they were giving me nonsense, which didn't match up with what I'd understood it to be. So unfortunately, it is one of the sad cases where even as teachers, there's certain aspects of science that we didn't learn correctly. Okay, and unfortunately we tend as teachers to continue teaching those, which is why it's so important, I think, for all teachers that we constantly reassess what we know and what's really true versus what we think is true. All right, so there's a question here, what are the spectator ions? I wouldn't even be talking about spectator ions, but whichever side of the salt didn't react, that would just remain behind as a spectator ion. We usually only refer to things as spectator ions when we're dealing with our electrochemistry, because then it's redox and they don't change oxidation numbers. All right, so what we're going to do now is we're going to jump into our past paper questions, and I'm going to give you an option or an opportunity to do this. Now, this question over here is a nice straightforward 5-mark question. So it says the reaction between hydrogen chloride gas and ammonia produces ammonium chloride crystals. And I'm going to ask you all very quickly if you can just quickly answer those 5 marks worth of questions. From what we've been doing, it should be really nice and straightforward. All right, so I'm going to pause sharing. I'm going to write down my answers and then I'm going to check in on all of you. All right. All right, if you can give me a thumbs up when you're done. Okay, good. Make sure that you read the very first question correctly and you don't jump to the wrong conclusion because you're talking about the wrong substance. Okay, I don't think you should need too much more time, so I'm going to start getting ready to go through the solution. So quickly get yours all written down so that we can compare. All right, so let's go through this. So the first thing that I did is I said it's a reaction between hydrogen chloride gas, which is a strong acid, and ammonia, which is a weak base. It produces ammonium chloride crystals. Is the ammonia solution a weak or a strong base? Please, we're talking about ammonia. We're over here. We're not talking about ammonium chloride yet. So the answer is that it is a weak base. And the reason that any substance is a weak base is that it ionizes only partially in solution. You may even want to say ionizes only partially in solution to generate or to create or to produce a low concentration of H3O+. But usually we'll give you 1 mark for ionizes partially in solution and 1 mark for the low H3O+. And since this is only out of 2, we usually accept either the ionizes partially in solution or the low concentration of H3O+. The ammonium chloride dissolves in water. Will the resultant solution, which is your technically hydrolysis of your ammonium chloride salt and its reaction with water, will it be acidic, basic, or neutral? Well, I went back to default here. It's between a strong acid and a weak base. Strong acid of the solution wins, so it's going to be an acidic solution. Then I could have looked at these, and I'm going to look a little bit messily here, but the strong acid means that the Cl- is a weak conjugate base. The weak base means that the NH4+ is a strong conjugate acid. So I'm going to react my NH4+ as an acid. It will donate an H and a plus, leaving us with NH3. The H and the plus joins with the water to give us H3O+, and that for 2 marks is the solution. Sometimes we're super nice and we've got to split this down the middle, and we give you 1 mark for this side and 1 mark for this side. But please note, anything like a plus left off or the wrong number, if you made this NH3+ or anything that's wrong with it, will lose you 1 of those 2 marks. Sometimes it's 2 or none, so they can do it either way. All right, ladies and gentlemen, who got that correct? All 5 marks. Yay. Okay, fantastic. For those of you who didn't, please make sure that you read carefully. I think the most probable place where somebody went wrong is they misread the ammonia right at the beginning as being ammonium chloride, and they got very excited, or they hadn't learned what strong and weak acids and bases were and which were which, and then they got a little bit muddled from there. All right, let's go back and let's do the next question. Now, we've got just over half an hour, and I've got quite a large number of questions, but I think I'm going to try and get through all of them because I think they're really good questions. And I also think that we may manage to get through these a little bit faster than I imagine. Whew, all right. This question, I think, is a particularly nasty one, so I may jump ahead. How do we know that the ammonia was weak? You're supposed to know that off by heart. It's your list of which acids and bases are strong or weak. I'm going to skip, no, actually, maybe I shouldn't. 7.2 follows on from this question, and it's just a very complicated question. So if everybody's good, I am going to do it, but I warn you, there's lots of bits to it, which makes it a little bit challenging. Okay, so let's just quickly check. We've got 2 beakers, so I'm going to have to zoom in. I hope everybody will continue to be able to see this, so that I can see all of my questions. Okay. Can I just quickly double check? Can everybody see that writing clearly? Okay, well, you could before I put my thing in the way. There we go. Okay, so what we're going to do with this particular one, it is a challenging question. I know this fully. I'm going to try and guide you through it bit by bit. I do want as much as possible to give you an opportunity to check each question and to answer each question as we go. So it says beaker A contains 44 centimeters cubed of hydrochloric acid of unknown concentration. So we don't know what its concentration is. And beaker B, here it is, contains sodium hydroxide of unknown concentration. Oi, I just suddenly remembered this is a super nasty one. Okay, so I may give up on this at some point. We'll see how we go. So you are told that a learner performs 3 experiments with the reagents above. So in experiment 1, the learner adds exactly 5 times 10 to the negative 3 grams of pure calcium carbonate to 36 centimeters cubed of the hydrochloric acid from beaker A, where we don't know its concentration. The calcium carbonate reacts completely, and the learner establishes that the HCl was in excess. That means that there is more HCl than we need. Okay. The balanced equation for this reaction is given over here. Okay, so that is experiment number 1, where we take 36 centimeters cubed. You'll notice we start with 44 centimeters cubed, which means we are not using all of the HCl in beaker A. So we don't know its concentration, and all that we know is that there's more of it than we need. I warned you this question was one that kind of blew everyone's minds. Okay, it's one of those delightful questions. Experiment 2 says, now experiment 2, we didn't actually know, I don't think we knew what volume it was. So in a titration, exactly 25 centimeters cubed of the sodium hydroxide is required to neutralize the 36 centimeters cubed of excess hydrochloric acid that is left over from experiment 1. So that is what we're then reacting this with. Okay, and the last step, in another titration, exactly 10 centimeters cubed of the sodium hydroxide, that's the original sodium hydroxide of unknown concentration, is required to completely neutralize the remaining 8 centimeters cubed of the original HCl. If you remember, we took 36 centimeters cubed of this here, so we're left with 8 centimeters cubed, and that 8 centimeters cubed is neutralized, and here's the balanced equation. So here is the reaction for both experiment 2 and 3. One which happens with the HCl that has been pre-reacted with calcium carbonate, and the second one that happens with pure strength, full concentration of HCl and NaOH. All right. Now, I want to start at this point by asking who's already finding this question a little bit overwhelming? Anyone? Okay, don't worry. I should probably put my thumbs up as well, but I can't find it. It's on the previous. It is a confusing question. And I warn you, I know the first time I saw this question, I actually wasn't very comfortable with it either. But when we see a question that's this challenging, the biggest secret is to breathe in, breathe out, and then try to solve it. Don't beat yourself up with getting to the end point. Focus on what you can do en route, because a lot of the time people get so flustered by the question that they forget to do the marks that they can get easily. So let's go and look at the marks that we can get easily. These marks, believe it or not, all 4 of them, this is only a total of 13, so we can get 4 out of our 13 without any stresses here, is to work out the number of moles of HCl that react in experiment 1. Please note that react, not that are left over. So what we're going to do is we're going to use the mass of our calcium carbonate, and we're going to work out how many moles of calcium carbonate react. Since we know the mass, we can work out the number of moles that react, and then these are in a ratio of 2 to 1. So from that, you can work out the number of moles of HCl. All right, so everybody, your steps, quite simply, because I am going to make you do them on your own, are to work out the number of moles of calcium carbonate, and then use your mole ratio to get the number of moles of HCl. Confusing as this whole question is, you definitely could do that bit. All right, so I'm going to pause my screen and give you a chance to work that out, and then we'll compare our answers. All right. All right, once you've got an answer, thumbs up. Fantastic. Probably more important, if your answer is 1 times 10 to the negative 4, is that better? Is that a good thing? All right, let me quickly resume my share with all of you. So the molar mass of calcium carbonate is 100 grams per mole. 5 times 10 to the negative 3 divided by 100 gave me 5 times 10 to the negative 5. That is the number of moles of calcium carbonate, but I needed the number of moles of HCl, which is twice as much. So that gave me 1 times 10 to the negative 4. Quick show of thumbs who got that one correct. Okay, maybe you're just taking a little while there. Okay, good. There are all the thumbs. Cool. The next question that gets asked here, you can immediately tell is a little bit trickier because it asks us for the pH of the original HCl solution. Now, the problem with this is if you don't know the concentration of the original HCl solution, you're not going to be able to go very far with it. So, in order to do this bit here, you need to do quite a lot of working backwards because what we need to actually know is we need to know what is the concentration of the original HCl solution. Now, this step here is where things get a little bit nasty. So I'm actually going to work some of it with you, and then I'm going to leave you to do the pH once we got to the concentration. So we can work with simultaneous equations from these two reactions, okay? So if I look at my balanced equation here, I can use, since they talk about neutralize, this reaction involves neutralization. So in experiment 3, I may say CaVa over CbVb is equal to Na over Nb. Now, I don't know either the concentration of the acid or the base, so I'm going to call this one Ca, and I'm going to call this one Cb. Don't know what they are, okay? I'm just going to use them, and I'll use capital A and B to differentiate them from what we actually had here. Okay, so let's start. The concentration of the acid I'm going to leave blank for now because it gets a bit messy, but the volume of the acid is 808. Concentration, if we're dealing with the original HCl acid, I can do that one. It's the original HCl acid, I can make that concentration of acid that I didn't know. Its volume is 8. Concentration of the base, I didn't know, but it's going to be called Cb. And the concentration of the base here is going to be 10. And if I look at this equation, it's 1 to 1. So therefore, from that, I can see that 8 times the concentration of the acid is equal to 10 times the concentration. Let's just undo that. That's a bit big. Concentration of the base. Okay. If you want to be good with your maths, you can then go and neaten this up a bit and say that the concentration of the acid to the concentration of the base is in a ratio of 4 to 5. Okay. There we go. You could even do it a ratio where you say the concentration of the acid is equal to a certain ratio of the base. But since I'm going to start by wanting the acid, I'm actually going to do it the other way around. So I'm going to say that the concentration of the base, let's quickly neaten this up, the concentration of the base is going to be 4/5 the concentration of the acid. Okay, that's equation number 1. Then I have to think very carefully here. Now, what they did, from my understanding, when I last went through this, me having to remember how this question was solved because it was that nasty, is that I think that the number of moles, we did a cheeky thing where we worked with from the number of moles to the concentration. And it really wasn't a very comfortable thing because I wanted to convert all of these from concentration into volume, and then it got so nasty. All right, so what I'm going to do here is I'm going to do the same thing with the second titration. Okay, bear in mind we may not get to the end of all of this. It was a very, very messy version. I still remember that. Okay, so the second version is CaVa over CbVb is equal to Na over Nb, but this is now going to be for the original with the excess HCl. All right, so I'm actually going to do this rather in terms of concentration. I am very tempted to do it in terms of moles. You all know that that and that are equal to the moles. Okay, so what I may choose to do here, because I want to talk about the number of moles. This is the number of moles of HCl which reacted. So the number of moles initial for my HCl, I could have written that in either order. Number of moles initial would have been the number of moles that were in excess at the end here. Okay, so I can say that the number of moles initial are the number of moles initial minus, no, wait, wrong way around. Sorry, let me just get my head wrapped around this. This wasn't my favorite question to do. So the number of moles final is equal to the number of moles initial minus the number of moles that reacted. Okay, my number of moles final is going to be the concentration of this acid here. Okay, so when I plug it in there, it's going to be there. And the number of moles, if I were to change this to concentration, concentration is number of moles over volume. So I can say that the number of moles is equal to the concentration multiplied by the volume. So at the end, it's going to be Ca, let's call this 2. This is where this question gets nasty. Its concentration multiplied by its volume. So I know at the end, I have got, where are we? 36. Okay, now I should technically, and I'm going to be good because this was correctly in the number of moles here, I'm going to turn this 36 centimeters into a 0,036 moles. The number of moles initial is going to be the Ca, where are we now? Ca original there times by the original volume that we added right over there, which is still the 0,036, okay? And then over here, this is going to be minus the number of moles that reacted, which is 1 times 10 to the negative 4. All right. Whew. So, I don't know if that makes sense to everybody, that we're doing a mole ratio here, saying the number of moles that you finish with are the number of moles that you start with minus the number of moles that react. That's the number of moles that react. Now, what, oh wait, yes, that's number of moles, number of moles. Now, what's important here is that the volume doesn't change, okay? Sneaky, sneaky thing that's happening there. All right, so we can get a little bit of information here about how these two ratios link to each other, but I'm going to leave that just for a second. I know that this is a nasty question, so I just want to kind of get you around to where we might be able to work for it. Just so you know, in case you're panicking right now, if you write pH is equal to negative log concentration of H3O plus, you've already got 1 mark. So if you're breathing in and out a little bit fast right now, there's 1 mark for writing that. There's 1 mark for doing that. There's 1 mark here for doing that substitution. Okay, so we've already got 3 of our 7 marks, even with us being completely lost with all of the other bits. Whew. So we're now going to go and jump in here with as much information as we can get. Now, I really don't like doing this bit, but I'm going to do it. So I got the concentration of acid 2 is going to be 0,036 times by Ca, okay, minus 1 times 10 to the negative 4 divided by 0,036. This is where it gets super nasty. All right, so that over there is what I can plug here for my Ca2, 0,036 Ca minus 1 times 10 to the negative 4 over 0,036. Okay, that is all for Ca. VA, this was in this step, was going to be the excess HCl. So we can go and multiply this by the 0.036. Okay, you'll see that those cancel out. The concentration of our base, we don't know, but we know that it's 25, so it's 0.025 times, I guess I didn't have to do these converted across, but it's okay, 0.025 multiplied by the concentration of base, and that gives me a ratio of 1 to 1. Now, this particular question, I remember getting very confused with, because what the memo, if I'm correct, ended up doing was it actually looked at everything and it just said you could convert from concentration to moles, ta-da, and you didn't have to worry. If I remember correctly, it had something to do with those values, and that we could just assume that it went 36 the whole way across, but I'm not quite certain. From here, what we then went and did was a simultaneous equation. We've got a CB on its own and a CB on its own, and we rearranged and we solved for the original concentration of acid. Okay. Can I ask, who have I lost? Anyone already been lost? Yeah. It is a very, very nasty question. Don't worry, if I've lost you, it's okay. But who, okay, before I ask the who have I lost, because this question wasn't my favorite when we did it the first time. Who kind of feels like they understand the steps in isolation? So you understand that you can work out that the final number of moles is what you started with minus what you used. And that you can do a simultaneous equation where you work with CAVA over CBVB that twice for the one reaction that had the full solution strength and the one that had the reduced strength. The good news in an exam is that all of the little bits that you link together do add together to make a whole solution. Okay, so I'm not going to go into the full detail of the maths with this. I remember when I saw this the first time, I actually thought it was a really impossible question. Okay. This was one of the questions that came out of last year's prelim. So it was a super nasty question, which you'd hope they don't give you for a matric exam, because this is 7 marks worth, but I think it's actually worth quite a lot more. Now, just so you know, all of the marks are not lost. I'm not going to carry on doing all of the equations here, but I am going to tell you what I would do. So let's pretend that at some point, we figure out that the original acid's concentration was 0.1. Good news, even if you don't figure out what it is because the maths is really hard, write down with quite certain values at some point that you believe that the concentration of HCl initial is 0.1 moles per decimeter cubed. You're allowed to do this because you get your substitution marks. So if you randomly come up with a value and then you plug it in appropriately, so you write negative log 0.1 times 10, or what would it be? It would just be 0.1. Let's not put in extra values. 0.1, and then you work out your answer properly. You can still get all of your marks. So please don't panic about things not fitting the whole way through. As long as you've got most of the bits, it's good. Okay, so that was the first. The second bit here is, doesn't matter what answer you got here, if you use this ratio to work out the concentration of base, you get your marks here. So if I worked out that this eventually was 0.1, I can then jump in and say that the concentration of my sodium hydroxide initial is 4/5 of the 0.1, which is going to give me 0.08 moles per decimeter cubed. So you'll see that even though this question is horrible, I warned you at the beginning about the brain feeling a little bit stretched, okay? Even if the question here is particularly horrible, okay, you can still get your formula marks, 1, 2 of them, substitution marks, 1, 2 of them, okay? So far we've managed to get probably at least 4 of the 7 marks without really doing any maths, okay? You might have got this one from some version of the subtraction there, okay? So you can see that you can build up the majority of those 7 marks without necessarily knowing where you're going. And provided that you got to this ratio, which I think most of you out of all of the calculations here, this one here was probably the most obvious to get to. From there, you can also get your last 2 marks. Please, even if you didn't come up with the correct ratio between the two, if you had any relationship between the two that was linked to this formula, then you could get the rest of the marks there. All right. Yes, you are allowed to use the ratios, but the problem is that you would, when we talk about using the ratios as to how much of them react, you've also got to bear in mind that the second one had 1 times 10 to the negative 4 moles removed from it, but you don't know what its original concentration was, which is where it gets very nasty with this, is that you know that this changes and you've got a smaller volume. You can, with any of these questions, if you can do it using decent ratios, you can get all the marks. So ladies and gentlemen, I'm going to ask you to quickly take a screenshot of what we've got here. I'm going to be very nice. I do have the memo to this particular question, and I will send you the memo out a little bit later. Okay, so I'm not going to keep going through it because I think it may make some of you go a little bit insane with this particular one. All right. Okay. Let's quickly ask, who's ever seen anything this tricky before? Okay, good. 1 person. All right. I must be honest, this is one of the trickiest examples I've ever seen because usually they do not have as many unknown variables. So in this particular case, with them putting in an unknown acid and an unknown base, it didn't give you anything to hook your knowledge on, if that makes sense. Sometimes we like to be able to relate what we know to something that we don't know to something that we do. And here the problem was that you were doing everything in terms of variables and none of the variables were variables that you knew. All right, I know we're nearly at time, but I'm feeling at the moment like I've pushed you a little bit too far. So I thought we'd finish off. We may go a little bit over time, but with a question that at least everybody's able to do so that you don't feel quite so overwhelmed. Okay, so that was the end of this question. Here's the next question over here, sorry. Whew. Okay. I'm busy choosing between the 2 choices. Actually, let's go for a very easy one so that we all feel very accomplished at this. So I'm going to give you the last question that I've got done here because I think it's slightly easier than the one I had above. So you're going to hopefully feel a little bit capable with it. All right. I don't mean to. I sometimes find with these when you do the very, very tricky ones, it has the habit of kind of demotivating everybody. So everybody gets to the point where they want to go home and cry. Please don't go home and cry. All right. So let's have, sorry, it keeps moving me around here. We're going to finish off with this question here. Okay. So the question says the concentration of hydroxide ions in a sample of pool water at a temperature of 25 degrees Celsius is that much. Okay. So the first question for 3 marks is to calculate the concentration of the oxonium ions. You're used to hearing these as hydronium instead. So you're asked to calculate the concentration of the hydronium ions in the solution. Okay, I'm going to quickly pause my sharing and give you a chance to work this out. Go for it. All right, can I quickly ask who's already got to a solution? Okay, fantastic. So I'm going to quickly go and share this with you. You quite simply here, and a lot of people got very confused because they kind of are not sure what the formula is or where to work from. So here you could assume that the kW value at 25 degrees Celsius is going to be 1 times 10 to the minus 14. So you can't work with temperatures if it's not 25 degrees Celsius unless they give you the specific kW for another temperature. So they can give you a kW value for any temperature, but you wouldn't be able to work with it at another temperature unless you were given that. All right. So that over there was the first step. I think most of you should have been relatively good with this. Please, you can rearrange before you do your substitution, but it'll be formula, substitution, answer with units. The next question is to calculate the pH of the sample of the water. So I'm going to quickly pause it while I give you a chance to work that out. Okay, can I quickly just check who's got the answer ready? All right, good. Okay, oh, let's move that. So I got an answer of 8.5. Please double check with your values that they always make sense. We expect this particular solution here, because we had a concentration where there was more hydroxide ions than hydronium ions, we do expect it to be basic. I'm giving you a bit of a heads up here. So next question says, should pool acid or sodium carbonate be added to the pool to bring its pH closer to 7? Okay, I'm going to let somebody shout out the answer for that one because it's rather straightforward. Anybody prepared to shout out?
Pool acid.
Yay, we're going to add pool acid because we're in a situation where our pH is too high, it's too basic. All right, so the reason that we're going to be adding in pool acid is that we need to lower the pH, therefore add pool acid. I guess they probably would have had to be pretty lenient where if you did say that sodium carbonate is a basic salt, that you could probably have said that if you added the sodium carbonate, it would make the pH even higher still. So with a question like this, there are often multiple possible answers that you can put in that will take you around to an answer, even if it's not necessarily the correct one. All right, can I ask everyone to quickly take a screenshot of what they need? All right, and I'm going to stop sharing there. All right, ladies and gentlemen, I know that we've done quite a lot of brain taxing work today. I know my brain is definitely pretty exhausted from that in-between question, especially when it came to the maths bits. I knew it was going to be pretty messy. Just one last thing before we finish off on the section of acids and bases. Please remember that you can only use the equation CAVA over CBVB is NA over NB if you have a solution that gets neutralized. You cannot just have it if you throw in some acid and some base. They're not going to react in the exact ratio always to become neutral. So one of the biggest mistakes that people make is that instead of viewing those kind of questions from number of moles, and that the fact that you can have an excess number of moles of either acid or base, they try to always use that equation which they associate with titrations, and it gets very messy from there. All right, so please just be aware of that. All right,